nucleus. When I compare the stability of a nucleus, what I see is that this is the n equal to z. So the stability curve initially for lighter nuclei will be n equal to z. For heavier nuclei, it will favor n greater than z. So there are two parts are there. O, A, OAB like this. So this is OA, that one. Look at this OA will become lighter nuclei. So if you look at the nucleus, lighter nuclei, they will have n equal to z. For lighter nuclei, for stability, they prefer n equal to z. Heavier nuclei, for stability, they prefer n greater than z. So when I check like this, there's a stability curve. When I check it, no, all the nucleides are not stable. Even lighter nuclei, few are unstable. So suppose say like a here, I'll write the number 1. Okay, 1. I think in the books they're given this way. Let me write. What is the dots? What are the dots? Dots are the nucleides. So what we see that there are some nuclei. Let me show few outside. It will be meaningful. If you look at the lighter nuclei, all the lighter nuclei are not stable. Few what happen, those which are stable, I see that n equal to z. And few what happen, the lighter nuclei n will not be equal to z and they're not stable. And when I go for the heavier nuclei, n greater than z, no doubt. Then though n greater than that, still what happens, some heavier nuclei are not stable. So is it all lighter nuclei stable? No. Those which will lie on stability curve. What is the stability curve? This region is what? Stability curve. I'll shade it. There's a region and you have to extend that yellow color line till further here. So that what all you see yellow, that is the stability, that one. So yellow color shaded. Shaded region indicates stability. Is it all lighter nuclei stable? No. Few are lying outside, no. And is it all heavier nuclei stable, though n greater than that? No. Few are lying outside. You can see this. You can see this. So here will indicate few more. Getting this one? So is it all lighter nuclei stable? No. Though n equal to z and some what happen are satisfying n equal to z stable and some what happen slightly n. Suppose it 4 protons, 4 neutrons. So some are having what happen like a 5 protons and 1 neutron. So like a 4 neutrons. They're not stable. So all lighter nuclei are not stable and all heavier nuclei are stable. So n greater than that. But what is happening? Most of the heavier nuclei where n greater than that, they're stable. And look at the lighter nuclei where n equal to that, they're stable. But all lighter nuclei are not stable, though n equal to z. So this shows that there is some stability, just you can't define with this particular condition. No? In nuclei, what happens? Lighter nuclei to attain stability, it will prefer n equal to z. Heavier nuclei to attain stability. Why n greater than that? Because if more protons are there, those protons which are at nearby the surface of nucleus, diametrically opposite, their interactions will be very poor. No? and the stability of nucleus will decrease by very large amount. So then it lead to instability, that one. So prefer, so therefore what the nucleus will do, it will try to have more neutrons than protons, as in fact we see that one. But all heavier nuclei are not stable, all lighter nuclei are not stable. So few where n equal to z, they're stable. Few nuclei where n greater than that, they're stable. But all heavy nuclei are not stable. So therefore this particular the line, what is this line? N equal to z. I think it's not expressing the, it will not exactly telling us the information. No? What we have to give reason why, though lighter nuclei they're having still some anywhere n equal to that, why they're still unstable. Though heavier nuclei they're having n greater than that, why they are unstable. That explanation we have to give. So for that weapon, we'll go for binding energy per nucleon. We know how to calculate binding energy. Like that, I'll calculate binding energy per nucleon. The binding energy per nucleon is what? Giving explanation. Those particular nuclides where binding energy per nucleon is maximum, they are said to be stable. So shall we put a condition that all lighter nuclei are not stable, though n equal to z. All heavier nuclei, though n greater than z, are not stable. So definitely this curve is not at all explaining us anything that why few are stable, why few are unstable. So it's of not much use. It will not give exact reason here. So what is the conclusion? I'll make it. All lighter nuclei though n equal to z. All heavier nuclei are not stable though n greater than z. But what I see, there are few nuclei where n greater than they are stable. I think this is not something exact reason. No? Are you trying to understand? Stable means they don't further, they will remain as it is. Huh? Iron is there, should be iron only, even after 1,000 years, 10,000 years. Gold. It should not become silver. It should be gold only. There's the meaning of stable. All nuclei are not stable, though n equals z. All heavy nuclei are not stable, though n greater than z. So this is not exact reason what we can. But the nuclear, what happen? Heavier nuclei will try to prefer more neutrons than protons for stability, but still they are not stable. So therefore, what is the reason now? So how to express the stability? The stability what will go for binding energy per nucleon. With the help of that curve, we can define the binding energy, the stability curve very easily. So we can give exact reason. So those nuclides which are having binding energy per nucleon more, and they are said to be stable. And those nuclei which are having less binding